Welcome to Stars, Cells, and God. This is a show where we talk about new scientific discoveries that give us additional evidence for the Christian faith. And you can follow us on social media. RTB_official is your gateway to all the reasons to believe social media outlets. And, all of us scholars here at Reasons to Believe maintain a Twitter and a Facebook page. Jeff, you got a Facebook and Twitter, and you take questions. I take questions. We all do. So if you got questions, feel free to contact us on Facebook and Twitter. And Reasons to Believe has a 24/7 YouTube channel. You can subscribe to it for free. And this episode will be posted, so you can watch it weeks later. You can share it with your friends. And literally, there are thousands of video clips from Reasons to Believe that you can access on our YouTube channel. So please take advantage of that. And reasons.org is our website. And there's literally thousands of articles there that you can access for free that keep you up to date on what the book of nature is revealing that tells us that the book of Scripture is the inspired, inerrant Word of God. Jeff, let's begin with you. You've got something, at least from my perspective as an astronomer, I find quite disturbing. But tell us what it's all about and what we can do about it.
Well, I will say it has nothing to do with whether astronomy has shown something in the Bible to be inaccurate. But what I find interesting is that we just recently launched the James Webb Space Telescope, and this is like the Hubble, the best optical infrared telescope that will have launched. Just phenomenal clarity. I mean, I've seen some of the preliminary images of just as they're tuning it up and making sure it's running, and what we used to be able to see and what we will now be able to see.
Did you see that one where they compared the Spitzer infrared telescope with the James Webb and the tremendous difference?
Yeah, I haven't seen that, but I mean, what I did see was like, wow, that's spectacular. And I remember even when they launched the Hubble, even when it came back and it wasn't working properly, it was still better than everything we could do from the ground. And then once we tuned it up, I mean, it's just given us phenomenal results. And, satellites are just an important part of astronomy, but most of the satellites that are up there, a whole lot of satellites that are up in space actually are not astronomy related. And they do things like provide us the GPS that allows us to navigate around the globe, drive our cars that our cell phones use to tap into that information. And for most of at least the past 100 years when we've been able to put satellites up, there's been, the scientific use and the commercial use, if you will, have largely not impacted each other. And there's been a lot of work to make sure that the radio emissions from telescopes lie outside the range of our radio telescopes. And there just hasn't been too many of them. And one of the things I found as I've looked into it is that if you go back a couple of years and ask the question, how many satellites are up there? There's something on the order of a few thousand. I think last I looked, it was about 6,000 in 2021. And the bulk of those, or the largest owner of those, is actually Elon Musk's SpaceX constellation. It had about 1,600 of them. So, you think there's about 4,000 satellites that were not related to that large commercial endeavor. So there's not a lot of them is what that amounts to. But when you look at what SpaceX wants to put up, roughly 40,000 satellites, and that now starts to change the look of how space looks. And I got a little graphic, if you could advance the next one here. This is there's a Vera Rubin telescope that's going to be built on the ground about 30 degrees latitude. And on the top right there, this is what it would see in terms of satellites in the sky just after sunset, or before the sun comes up or goes down. And you see on the left there's a few streaks floating around, but largely the image is pretty open. Well, if you now add SpaceX and Project Kuiper and OneWeb, which are three constellations, it's Amazon is Project Kuiper. OneWeb, I forget who actually owns that one, and then SpaceX. Now you get what's on the right. This is what the Vera Rubin telescope would see. And what was a few blips that are annoying now becomes just a dominant structure of what's there.
How many satellites total are we talking about?
For SpaceX, they want to put up about 40,000.
40,000. What about these other arrays?
So all of those put together, 40, 50,000, somewhere in there. But SpaceX is not the biggest market out there or the biggest contributor to this. I mean, I looked in there, at least one, Rwanda, China, wants to put up 13,000 satellites. Rwanda wants to put up 327,000 satellites. And there's a Canadian Kepler Communications company which wants to put up 115,000.
So now we're looking at about 500,000 satellites orbiting the Earth.
Yes, and that doesn't account for, some of them will come down, they'll continue to be going up, and as they deorbit, they generate space junk, and there's a whole problem, it's going to be very crowded up there. And you're starting to see there's this tension between putting, what Elon Musk is trying to do is provide internet access to everybody. So it's not like he's just out there, ooh, I've got a lot of money, let's take over space. This is to provide services to people here on Earth, and something that is increasingly being seen as a fundamental necessity for operating in society is good internet access. Well, that's what Elon Musk is trying to do, and these other companies are saying, hey, we can provide this sort of scenario or this sort of utility to get up. I've talked a lot about the metaverse. Well, one of the ways that you're going to be able to engage the metaverse is you got to have good internet connections, because that's how you can connect with people.
And there's a commercial incentive here too, because for sure they're going to be selling advertising.
Oh, of course. I mean, obviously there's going to be some financial recourse to doing this, but the kind of the what I want to get across is this is not just, ooh, let's go out and make money. This is people that are trying to provide stuff that increasingly we see as important in society. The ability to engage on the internet, the ability, to engage in the metaverse, because that's where commerce and society is going to happen. And
well, with this, there'll be no more lost hikers, right? I mean, you're going to know exactly where you are. It's going to be public. So.
Well, unless you decide to not carry stuff around that tells where you are, but those are the sorts of things that are going out. I mean, I just saw, there's a relatively recent ad on TV where a guy's biking along in the forest and he falls and injures himself, and so his phones or whatever, some electronic device he has, starts sending out signals saying, "Hey, this is where I am. This is how to come," or the car runs over the edge of the road. So these safety services and internet access and other services are all powered or made possible by these sorts of satellite things. So it's, like I said, I want to get across the point. This isn't just, ooh, let's see what we can do in space and have fun and see if we can make money. This is providing services that increasingly people think are very, very important. But you have this tension between providing those services requires putting up all of these satellites, which are going to make astronomical observations difficult, maybe even impossible, depending on how we do it. If you can go to the next slide, this is a slide that is a telescope that took a 2-hour observation. Granted, it's fairly wide field, so it's got a lot more in than some of the
This is way before these satellites were launched.
Yeah,
right?
This is what's going on right now.
Yeah.
So take this and make it 100 times more lines in it, and that's the sort of thing that our satellites, telescope communications, going to have to deal with, as well as our ground-based observations are all going to have to look through this. You could say, well, maybe we could just put up some space telescopes and get up above all that. But now that eliminates all, that dramatically impacts the number of people who can now engage in astronomy, because you can build telescopes in a lot of places across the world and get
for a lot less money.
For a lot less money too. No, that's a good point. And coupled in with all of this is all of these satellites, in terms of doing the communications, have to have radio transmissions to and from the satellites, which, as you know, impacts radio astronomy. And granted, we've carved out these little spaces where we say, okay, communications can use this, astronomy can use this band. But those were set a number of years ago, and astronomers, especially as we're looking further and further out in space, things are more distant. You redshift things to different regions of the spectrum, and you want to start covering more and more of that spectrum.
I did extragalactic astronomy, Jeff, and it's like all these protected bands, we're assuming astronomers are only going to be studying stuff in our galaxy. If you
Right.
go to other galaxies, those things are redshifted, which means they're no longer protected.
No, that's a good point, and it just kind of amplifies the point that I think people did a lot of work to try and figure out how can we allow these new satellites and radio telescopes, the technology that people are going to use, and astronomy to work well. But even now, we're seeing a tension with what was described then, and it's only going to be exacerbated by all of these satellites that are going up.
By a factor of at least 100, if not 1,000.
It really is, yeah.
Yeah.
And in some sense, you could just make an argument that, the amount of stuff that commercially needed to happen and the amount of astronomy was kind of small. And so they could largely play in different areas of the playground. Well, now the commercial is going to want to push into all areas of the playground. The astronomy is going to want to push into all areas of the playground. And we got to figure out how can this actually work. And it almost looks like we're forced into a choice of, do we do astronomy, which helps us understand how the cosmos works, or do we provide these services that take care of humanity? And we seem to be pushed into this dilemma. And what I think is fascinating is this is where what kind of view of the world we have comes into play. One of the comments I love that you made when you're talking about global warming is it's very often pitted as we got to take care of the globe or we got to take care of humans. And if Christianity's true, God has said, hey, humans are important, go take care of the globe. So there's got to be solutions in there that take care of humanity and the globe. And let's find those. I think there's something that would likely play out here because God has said, go out and understand the creation, but take care of the people in it. And so I expect actually there will be a solution in there. And that will point to the truth of Christianity.
One solution I see said, well, why don't you astronomers just depend on space telescopes like the James Webb, the Hubble Space Telescope, the Spitzer Telescope? But as a radio astronomer, what I'm saying, hey, you're overlooking the fact that a lot of our really big discoveries have been made by these very long baseline interferometers. And you can't put that in space, at least not without spending a huge amount of money. And so how do we protect these very long baseline interferometers that have been responsible for so much of the advances in astrophysics?
Well, and that even just raises a question, or raises the thought there, is that it's not that you can't do it. I mean, you just gave a solution to it. You can put a very long radio baseline interferometer up into space. It's just really expensive.
Yes.
And so now you're going to be asking this question, is the scientific gain we're going to have really worth that investment? Well, different worldviews are going to weigh in differently on that. I'm not going to say, naturalism is not just this, here's this little encapsulation of it. But if naturalism is correct, at some level you have to ask, what's the value of having a greater understanding of the cosmos? There's places where it touches in that the technology we develop often helps humans we can take care of humans and the planet better. But when you're talking about the types of resources, instead of spending a couple $1 million and building a really quality ground-based telescope, you're spending hundreds of millions, if not billions, to put that equivalent telescope up into space. That's a very different conversation now. And your worldview really needs to provide the foundation of why that's important. And I think the Judeo-Christian worldview does, because science is important, because it helps us understand God's revelation and know him better.
Well, you know what? I read the article that you're citing. I was thinking, this is going to make a lot of money for people like Elon Musk. We're talking tens of billions of dollars of profit.
Mm-hmm.
Could some of that be diverted to, hey, you astronomers are going to have a lot more funding to put these things into space? Is it possible that we could come up with some kind of win-win saying, okay, launch your 300,000 satellites, but we want to ensure that some of the profit goes towards funding the astronomy that can no longer be done inexpensively from the ground?
I agree. And, one of the things that the article did mention is that a lot of astronomers are trying to start engaging with and this is not new, they've been doing this all along, but really working at engaging with the people who are trying to launch these constellations trying to develop that kind of, hey, we both want to do this well. But Elon Musk could very easily say, hey, this is just important. I found a good economic niche here. I can do this. What worldview he adopts is going to influence how much he wants to engage with people. If it's, hey, I want to get what I can and take care of myself, unless we come up with laws or rules to do otherwise, and laws and rules work to some measure, but they don't change the heart, if you will.
Well, and moreover, it's hard to do it internationally. I mean, you got Rwanda wanting to put up 350,000 satellites. So
yeah, so now you've got geopolitical stuff that comes into there, and Rwanda isn't necessarily a world player in terms of power of how things go on in the world, but now, say you got that same sort of thing with China wants to do and the U.S. wants to do. There's a competitive nature because who's going to be the world power? Yeah, there's just a lot of things that play in there, and those worldview issues, I think, really come to the forefront because those different countries do tend to, or the societies in those two countries tend to have different worldviews. And so which one do you do, and how do you find agreement or at least a way to work forward when you have such disparate ways of looking at the world?
Well, I am encouraged that people like Elon Musk are saying, you know what, we can make the satellites less reflective.
Mm-hmm.
So instead of getting a bright streak, you get a very dim streak. Doesn't help radio astronomers because you still got all that propagation coming to the ground.
Well, and the funny part was they made it less reflective, which caused them to heat up more because part of that reflectivity keeps the satellite cool. And so
right.
It's a fun engineering problem at a very real sense. But one of the things that struck me is in these sorts of discussions, I think you can make an argument that you want Christianity to be true because in a Judeo-Christian worldview, you do want to take care of people, but you also want to advance knowledge. And so when I'm going in, if I'm an Elon Musk, if I'm operating with a Judeo-Christian worldview, yes, I want to build technology. I want to make new things. I want to advance what we can do. But I'm also recognizing, hey, this isn't mine. This is here. God has gifted me with this. How can I use this to take care of others? And you would see the need of, science is important, so I want to invest in that. It would motivate, a Judeo-Christian worldview would tend to motivate people to want to take care of the others, not just their own interests. That's what Philippians talks about. Don't merely look out for your own interests, but consider the interests of others as more important than yours.
Yeah, and if God's all behind this, we will be able to find win-win solutions, but it means we might have to work pretty hard to find them.
Or they might be very costly, but nonetheless, we're going to have the resources and we're going to be doing it. And Christianity, if it's true, this is why I want it to be true, is because Christianity provides the framework, the way of thinking about things so that you're looking at how can we solve these problems instead of how can I take care of myself and get mine,
Sure.
which a lot of other worldviews tend to have that as the forefront of what they're thinking about. So,
Well, I'm also wondering, Jeff, if these Starlink projects, maybe there's a way to pull us off by using really tiny satellites instead of big satellites. I mean, we've been doing remarkable things with miniaturization.
yeah.
Is that a possibility? And do you really need 300,000 satellites in your Starlink network? Could you get by with fewer? Maybe there's a way that you can keep the thing cool and still keep it low reflective. I mean, what are your thoughts on this? Do you have any advice as to how we can push forward to try to get better win-win solutions?
I think a lot of that is what's the attitude we're adopting towards it. If it's, hey, we need to provide internet access to everybody regardless of the cost, then you got to realize the costs are going to be our ability to do astronomy in the future. Because the sorts of things, it's not just that all of these telescopes that are up there, satellites that are up there, but, if you also have a congestion problem, and we drive a lot in Los Angeles, and the moment some wreck happens, the traffic, which was already bad, gets much worse because that wreck now provides a whole lot a focus of a whole lot of other problems start happening. Well, say two of these satellites collide. Now there's a bunch of debris floating around, which means there's more opportunity for other satellites to collide, make more debris. And depending on how high you are, you could actually just completely make a particular range of space uninhabitable for satellites because there's just so much debris there, which would also curtail observations because there'd be stuff in the way.
A giant dust cloud around the Earth, that would be
giant
horrible.
Dust cloud. Well, and the satellites have a lot of aluminum because it's lightweight. Well, when satellites burn up in the atmosphere, they dump a lot of aluminum there, which hinders astronomy at certain wavelengths. And so there are all these secondary, and tertiary repercussions to having this huge spectrum of satellites up there, or constellation of satellites. And so what my encouragement would be is let's think about what worldviews allow us to think about this well. Because I think all of those technological problems are solvable if we decide they're important enough to put the resources and engagement behind.
And perhaps there's even more money for the Elon Musks of the world. I mean, what if they could put up all their satellites that are 5 centimeters across instead of 5 meters across?
It's cheap, less material.
Less would be cheaper.
Yeah.
And I mean, we can give them an economic incentive that would simultaneously help the astronomers.
Yeah.
That really could be a win-win. So,
the part of what I was thinking here is, an analogy. I've done some work on my house, and, doing work on a house in Los Angeles or the Southern California area is kind of hard. And it's expensive because you've got to you can't just build the wall up, put some 2x4s up, smack a wall on and call it good. You've got to put the 2x4s up, and then you got to put plywood on it and do everything, because I live in a region where earthquakes happen.
And an inspector is going to come by to make sure you did it right.
Well, and the reason they're doing that is because it's cheaper to put it up, and it works. And, I've lived in Los Angeles for close to 20 years now, and I haven't had any sort of earthquakes that really would be problematic. But if I don't build my house to those standards, that earthquake that inevitably is going to happen will cause great destruction in my family. So it's expensive for me to do. It seems like, why is that important? But if I know it's going to happen, then I can plan for it and make it happen. And I think that's true of what's going on here. There's going to be this tension of the more satellites we put up, the harder it's going to be to deal with the astronomy. The more we want to do astronomy, the more restricted range we have for the satellites. Both of those good interests need to be able to work together to find something that works for the common good of all of that, as well as future problems that we're going to solve. Because, right now we may not have the technology to put 5 meter or 5 centimeter satellites instead of 5 meter satellites. But, if we do that in the future, we're going to put a whole lot more of them, which means they're probably going to be more spread out. It may make the optical better at the expense of the radio or something. So there's all these things. We need to be thinking longer term, not just what works right now.
Right.
And again, I think that's a feature of the Judeo-Christian worldview, is it says, we're not supposed to just say, well, who cares what goes on in the future? No, you're supposed to plan for the future, but recognize that God's in control of what's going on. And so let's work according to what he's telling us to.
Yeah, I'm not sure what's happening in Rwanda or China, but at least what I'm seeing with the Canadians and the Americans is that they want astronomy to flourish.
Yes.
And so they're trying to work with the astronomers and saying, hey, how can we both be happy with what we need to see happen here?
Mm-hmm.
So it'd be different if they said, we don't care 2 bits about astronomy. We're going to put these satellites up. And if you're all out of business, that's just too bad. Fortunately, we're not seeing that attitude.
No, that is true. And I think that's partially because we see the benefit of the astronomy. You and I are both aware that the big discoveries or the advances in science, there's a lot of papers being published, but there you can make an argument that it takes a lot of work to get a little bit of results, because we've gotten a lot of the big fruit off the tree, if you will. And so what my question is, 50 years down the road, where it seems like, wow, you put a lot of money into astronomy and you get, you make progress, but it seems slow. Is that really worth the investment? And if you have this place where you really do need, or there's this big tension between, do we put satellites in the air now so that we can provide internet access, or do we continue to invest in astronomy, which may pay off 20 years down the road? what are we going to do there? And so again, I think the Judeo-Christian worldview has a great framework for thinking about that, and that's why I want to encourage people to really strongly consider it, because I think it provides the framework that allows us to answer all of these questions in a way that benefits humanity and our understanding of the
Well,
cosmos.
for example, certain satellites have made very long baseline interferometry more accurate and productive.
Hmm.
So it's like astronomers have benefited from
Hmm.
these satellites. But yeah, when I read what your article there is like, wait a minute, they hadn't even thought about how do we keep very long baseline interferometry going. To
Right,
me, that's a really big problem. We got some possibility of protecting optical astronomy,
right.
and we could protect to some degree, radio astronomy. We're only interested in low resolution radio astrophysics,
Hmm.
but it's the high resolution stuff that's been producing the really spectacular discoveries. How do we protect that?
And how do we protect what's going to be producing the results 50 years from now when we don't even exactly know what that's going to be? So,
Right, right. Okay. Well, this is good, Jeff. So, really appreciated reading that article and realizing, wow, this could happen in just a couple of years.
yeah,
It's like I thought, well, I was thinking this might be 20 years off. We got time to really work on miniaturizing these things, but they're talking about doing it soon.
yes, they are.
And I can kind of see some value for that. I mean, there's people in remote parts of the world that really need this internet access
Hmm.
and they don't have it. So I feel for those people, but I'm not really willing to say, okay, you astronomers, you better find another job.
Hmm.
So
Right.
maybe they'll be applying here at Reasons to
There
Believe.
you
Who
go. There
knows?
you go.
Okay. Well, the discovery I want to talk about, let me move on to this next slide here. It has to do with subdwarf stars. And Jeff, I don't know what it's like with you, and I talk to people about subdwarf stars, and what are you ever talking about? Is this a dwarf star that's smaller? No, or pardon me, they're talking about subgiant stars. My mistake. Subgiant stars?
I'm like, you can't get much below sub-dwarf without calling it a planet, but okay,
Right,
all right,
right.
that makes more sense.
We're talking about a subgiant star, and if people want to see one, they can see one tonight around about 9 or 10 o'clock in most parts of the world, because that's the constellation Scorpius, at least for Northern Hemisphere observers, is sitting low on the horizon
Okay.
in the evening. And that star at the end of the tail of the scorpion, Leseth, is a subgiant star.
Okay.
So Antares, which you can't miss, it's a
Hmm.
really bright red star low on the southern horizon. That's what we call a giant star.
Okay.
But Leseth is a subgiant star.
I presume subgiant does just mean not quite as big as giant.
Right. Um Giant stars are stars that are like 5 to 10 times the mass of our star, the sun, in that range.
Right.
Subgiants are less than 2 times the mass of our star, the sun.
Okay.
And they can even be half the mass of our star, the sun. But subgiants also refers to a time in their history. These are stars that have burnt through their hydrogen fuel,
Okay.
confusing hydrogen into helium, kind of like the hydrogen bomb process. But they've gone through all that fuel,
Hmm.
and now they're beginning to fuse helium into heavier elements. And so those are what we call the subgiant stars. Because when they run out of their hydrogen fuel, the star gets bigger. It loses mass. Nevertheless, it gets
Hmm.
bigger. So, like Antares, for example, is a giant star. It's so big that it would encompass the orbit of the Earth inside of it.
Right.
So
Okay.
it's a really big star. Subgiants aren't that big, but they're a whole lot bigger than our star, the sun. And this is what's called the HR diagram
Hmm.
that we love to really tease our freshman astronomy students with. It's basically what we call a color magnitude diagram, where you got the magnitude of the star, which is the brightness of the star. That's the y-axis. And on the x-axis, the bottom part, is the color of the star. And this basically shows you what happens to stars as they age. So that really big clump of brown colored stars that you see in the bottom, those are stars that are still fusing hydrogen into helium. We call them main sequence stars.
Well, one of the things that fascinates me about this, and you talk about color magnitude, and the reason why it's that is those are two things we can we can measure very easily with every star. We can look
Right.
and say what is its magnitude because that's a very straightforward measure, and then we can measure its color because that's the information we're getting. And so, you can't measure size with most stars because they typically just take up one pixel in a CCD, but you can measure both color and magnitude. So that's why we make this diagram.
Right. And this is an attempt to get the age of stars because this paper I'm talking about that got published in Nature is basically talking about how do we do galactic archaeology, which is basically looking at our Milky Way galaxy and determining what it was like in the past.
Okay.
And for that to be possible, you need to accurately measure the ages of stars,
Right.
which is where these subgiants come in. Because when you look at these subgiants, they're once they've moved off what we call the main sequence, where they're no longer fusing hydrogen to helium, they're moving into the helium fusion mechanisms. What you notice is they're getting brighter, and you notice it's almost a vertical line. All that brown stuff, uh, all those brown stars you see, there are stars that are less than 2 times the mass of our star, the sun. The bigger ones burn through their fuel faster, so you can ignore all the blue, the red, and the yellow, and the green. Those are the more massive stars. But what you notice is that once they stop fusing hydrogen to helium, you see that these subgiant stars brighten dramatically. And it's because they're getting bigger and bigger. And so they're getting brighter and brighter. But you can measure the brightness of the star, and that translates into how much time has gone by since they've run out of hydrogen fuel. So it's actually a way to get a fairly accurate age measure of the star. And I love what you said. Measuring the color is easy. Measuring the brightness of the star is easy. It's really difficult to measure the mass of the star. And that's kind of the limitation in trying to do galactic archaeology. For that to work, you've got to have accurate ages for the stars you're looking at.
So presumably, looking at this diagram, this is a whole bunch of stars, and presumably they're all in the same galaxy or same
They're all
cluster.
in the same cluster.
So we know how far away they are. So whether we know absolute
This is
magnitude.
the globular cluster M5.
Right. Okay. So what you've got there is, the big blob that kind of goes up and turns right. That's the main sequence until it turns right. But where it lands on there allows us to it allows us to get an age out of the star just by plotting it on this diagram because we have this population that we can look at.
That's correct.
Okay.
Yeah, in this particular globular cluster, you got quite a few subdwarfs. The problem is we're really interested in understanding the archaeology, the past history of our Milky Way galaxy is in the outer parts of our galaxy. And the problem there is subgiant stars are rare.
Okay.
There's not very many of them. And this paper is basically the first time that astronomers have come up with a big database of faraway subgiant stars.
Okay.
And
did the database is finding globular clusters out in the distant regions?
no, they're looking at individual stars out in
Okay.
the halo of our galaxy.
All right.
And they're very rare, but they basically took advantage of 2 recently huge surveys of distant stars and came up with a database of 250,000 subgiant stars. And to put that into context, the best we had until this paper was published was in the low thousands
Okay.
throughout what's called the thick disk of our Milky Way galaxy and the halo. And if all you got is a couple of thousand stars, it's difficult to come up with an accurate archaeological past history of the outer edges of our galaxy.
Okay.
So for the first time, because we have this enormous database of 250,000 stars, where you can measure the magnitude of the star, the brightness of the star, which translates into the age, which means we now have 250,000 stars where we got accurate ages. So that basically tells us when the stars formed. We know how old the star is. We know when it formed, and we can determine where it is in our Milky Way galaxy. So I'm going to move on to the, this is just another one of those slides. This shows you a couple of places where you can see the subgiants coming off of the main sequence. but I think, yeah, this is the one I want to show you. And, you know, excuse me for the rather lack of detail here. Uh, you can see that little black spiral stuff. That basically shows you the spiral arm structure of our galaxy. And then that light shaded part is what we call the thin gas disk
Mm-hmm.
of our Milky Way galaxy. And then that big, huge dark gray area is the dark matter halo that surrounds our galaxy. It's one of the unusual features of our Milky Way
Mm-hmm.
galaxy. It's got a huge amount of dark matter, and the dark matter halo, it's actually bigger than any other spiral
Mm-hmm.
galaxy that we've ever seen. So, and then this kind of shows you a side view, which basically shows you the flattened oblateness of the dark matter halo about our Milky Way galaxy. You get to see kind of the core of our galaxy, and then the very light gray part is what we call the thin disk, and then you got the thick disk, which is the black part. And so the disk of our galaxy, and there's a gas disk and there's a stellar disk.
Mm-hmm.
And so you got this thin gas disk, you got this thin stellar disk, and then overlapping it is a thick disk.
Right.
And we've known in the past, just based on a few thousand subgiant stars, that the thick disk is much older than the thin disk.
Right.
The thin disk is young, and we can measure the composition of the stars and see that the thin disk stars have a lot more elements heavier than hydrogen and helium than what we see with the thick disk stars. So that right away tells us the thick disk formed much earlier in the history of our galaxy.
So the reason behind that is that early in our galaxy's history, there weren't all the elements heavier than hydrogen and helium are produced through stars, and
Right.
so if you only have hydrogen and helium, that tells you that that the stars were born early in the disk. Whereas if you've got more and more heavier elements, previous generations of stars had to burn through their life and explode to seed the later ones. So
Yeah,
that gives
thank
you
you.
a rough chronology of when stars were formed,
Right.
just how much they have besides hydrogen
Yeah,
and
the
helium.
first few minutes of the Big Bang, you get some of that hydrogen being fused into helium and a very trace amount of lithium,
Hmm.
but everything else is made in the furnaces of stars.
Right.
And so, yeah, the younger the star, uh, the earlier it forms in the history of the universe, the less elements it's going to have that are heavier than helium.
Right.
Whereas stars like our star of the sun, which formed relatively recently, only 4.5 billion years ago, are going to have a higher quantity
Hmm.
because they've been enriched by the ashes of
Right.
died stars, dead
So,
stars.
so in the thick disk, you find a lot of stars with not much besides hydrogen and helium. In the thin
Right.
disk, you find a lot more besides hydrogen
Exactly,
and helium.
exactly. So, and this particular, this is the Andromeda Galaxy. It's called our sister galaxy because in the local group of galaxies, we've got two large spiral galaxies, our Milky Way and the Andromeda Galaxy. Then you got a bunch of dwarf galaxies. And, what we see here in the Andromeda Galaxy is you can see two dwarf galaxies, and these are called big dwarf galaxies. Most of the dwarf galaxies in the local group are quite tiny, but there are 5 that are big. And you can see kind of a little blob a little bit off to the left and above, and then you see one down to the bottom, which is bigger. But our friend in South Africa, David Block, he published a paper on this, basically saying if you look at the Andromeda Galaxy, you can see that the spiral arm structure is warped, and you got a lot more spiral arms far away from the center of the galaxy than you do in our Milky Way galaxy. And he was the one who did a study on the Andromeda Galaxy and these two dwarf galaxies and determined that that dwarf galaxy you see up above and slightly to the left of the center of the Andromeda Galaxy actually passed through the spiral arm structure about
Okay.
500 million years ago. And so he was able to demonstrate that's responsible for this really significant warp that you see here. It's also responsible for filling in the spiral arms with a whole lot of spurs and feathers. And it's all those spurs and feathers that would basically tell us, well, and maybe you could conceive of microbial life in the Andromeda Galaxy, but not advanced life. because of all those feathers and spurs between the spiral arms, the warping of the spiral arms, the disturbance of the spiral arms. That means that planetary systems like the solar system that would be in the spiral arm structure would be subject to significant gravitational disturbances, which means the orbits. One of the unique features of our solar system is that the planets have very close to circular orbits,
Right.
which is atypical. And you say, well, why do we need roughly circular orbits? Well, if you want winter not to be too severe and summer not to be too severe, you want to have a roughly circular orbit around the star.
Well, technically, you only need the planet where life is going on to have that sort of orbit. The other ones could be a little bit more.
They could be a little bit more, but if you want advanced life on a planet, and again, microbes are much more tolerant to this, but species like ourselves, we cannot tolerate a big difference in the temperature between winter and summer.
Right.
And we want to be able to grow the food that we need. And then, of course, when you get disturbances like this, you're going to get radiation events. In other words, you're going to have supermassive stars forming, and they're going to be pouring out nasty radiation, which could be deadly. And again, not such a problem for microbial life. They can handle a lot more radiation than we human beings can handle.
Okay.
So on this basis, we can look at the Andromeda Galaxy and say, well, it's hard to make a Star Wars movie based on the Andromeda Galaxy because of what we see there. But what this paper is basically showing is that the big difference between our Milky Way Galaxy and the Andromeda Galaxy is that our Milky Way Galaxy, what they did is they looked at these subgiant stars and basically said, when we look at the outer halo, and our Milky Way Galaxy is a complex structure. We got an inner halo and we got an outer halo, and then we got this thin disk and we got this thick disk. And what this study is showing is that the subgiant stars in the outer halo formed a long time ago.
Okay.
And about 11 billion years ago.
That's pretty close to when the galaxy itself formed.
Well, the galaxy, they also found some stars that date as far back as 13 billion years.
Okay.
And so they're basically saying the oldest subgiants are telling us that the Milky Way Galaxy was assembled, it formed at about 13 to 13.1 billion years ago.
Right.
And the last stars that were forming in the outer halo, that would be 11 billion years ago. And since then, it's been incredibly stable. So we don't, and they also see that the variation of heavy elements heavier than helium in these halo subgiant stars, very similar, not much variation as compared to what you see in the thin disk where you got a lot of variation, which tells us there's been a lot of star formation going on there. So it's basically telling us in terms of the galactic archaeology that in terms of the outer halo and the thick disk, it's basically been stable, undisturbed for the past 11 billion years. And this is an update. This is not new, but previous papers have been saying, yes, we see this stability, and they dated it to be 10 billion years.
Okay.
This is basically pushing it back by 1 billion years.
All right.
Saying that we're looking at, and then
So this is largely telling us that we've not had any significant encounters with dwarf galaxies passing through that would have been significant disruptions, other large galaxies that would have stirred up some sort of star formation out in the distant reaches, that our galaxy's been pretty stable is what that's saying, correct?
That's correct. And it's actually, they got enough data now to be able to definitively identify the two most recent big mergers of our Milky Way Galaxy with large dwarf galaxies. And 11 billion years ago, you got a dwarf galaxy that they call the Gaia. Let me get the exact term. It's the Gaia Sausage Enceladus. That's a really complicated name. I knew Enceladus, but it's called the Gaia Sausage Enceladus dwarf galaxy. And previous literature said the merger happened 10 billion years ago. This data is now coming up with a much more accurate date saying, no, it's 11 billion years ago that this happened. But the database is also telling us there was a smaller dwarf galaxy that merged with our Milky Way galaxy a little bit before the Gaia, Sausage, and
Mm-hmm.
Enceladus, which they call the Sequoia galaxy.
Okay.
So these two merger events, 11 billion years ago and about 11.2 to 11.5 billion years ago, were the last time that we had this. But to sustain the spiral structure, it is crucial that our Milky Way galaxy be getting a steady stream of tiny dwarf galaxies.
So it's not that we haven't had any mergers, but of these larger ones, like we saw on the bottom left and the top left of Andromeda, we haven't had anything of that scale. We've just had a lot smaller ones that have come through.
Yeah, when I say, we're talking like 10 to 100 times smaller.
Right. Okay.
And that brings in enough gas and dark matter to sustain the spiral structure.
Right.
So the problem with an isolated spiral galaxy, it's not going to be able to consume enough tiny dwarf galaxies to sustain the spiral structure, and the spiral structure collapses, and you get either an ellipsoidal or a spheroidal galaxy. And you say, what's the problem with that? Well, now you got the stars way too close together, or to have the possibility of an undisturbed planet orbiting a star where advanced life could exist without having deadly radiation. You really need to have a large spiral galaxy. Small spiral galaxies are going to be gravitationally beat up by the big spiral galaxies. And that's a unique feature of our local group. There's no giant galaxies that are going to pose a problem. And we are living in what we call a large spiral galaxy, well separated from many other big objects. But this paper is basically telling us there's been no significant gravitational disturbance of our Milky Way galaxy for now the past 11 billion years. And this explains why our spiral galaxy looks so different. Now, this is not a photograph or an image.
Obviously, no, I went and tried to take that picture last week, but I couldn't get far enough away. So.
No, that's the problem. You really can't send a satellite out 250,000 light years to take the image. This is a constructed map.
Right.
And what astronomers have done is they've taken, we were just talking about, hey, you got optical astronomy, infrared astronomy, radio astronomy. This map was constructed by astronomers taking the maps that they had produced at different wavelength ranges. So it's another argument for why we want to preserve not just optical astronomy, we want to preserve the entire electromagnetic band.
Yes.
Because with that capacity, you can take the different pieces. Because radio astronomers will map a different part of our galaxy than what the optical astronomers can do, or the infrared or the X-ray astronomers. But piecing it all together, they were able to develop this map. And this is a fairly high precision map of what our Milky Way galaxy looks like. But the obvious thing you see in this galaxy is how incredibly symmetrical the spiral arms are of our Milky Way galaxy. And you can also see, yes, there are stars between the spiral arms, but you're not getting these big feathers and spurs.
Right.
You do see a few spurs, but very few spurs. I mean, if you look off to the left center, you can see some spurs. Likewise, to the off to the right, you can see some spurs. But where our sun is happening to exist, real paucity of spurs and feathers, which is essential if you want to have advanced life. And this next slide shows you a collection of galaxies. What I've done is gone through the catalog of large spiral galaxies. These are galaxies that are roughly the size of our Milky Way galaxy and have the least disturbed spiral arm structure. So one of them is the Andromeda Galaxy, the one to the upper left. But here you're seeing other spiral galaxies at different orientations. But you notice in each case, it's different from what we see in our Milky Way galaxy. The spiral arms are either distorted, or they lack symmetry, or they got lots of spurs and feathers in between them. And here's 6 more. In the book I got coming out, Design of the Core, I show you the 18 galaxies that come the closest to matching our Milky Way galaxy. And a lot of people think the one in the upper center is the one that comes the closest. It's got the greatest degree of symmetry in its spiral arms. And notice there's not a whole lot of spurs and feathers, so that may be the best candidate for a Milky Way galaxy twin. But you can clearly see that the spiral arms are distorted, And moreover, this central bulge looks distinctly different what we see in our Milky Way galaxy. And here we are with our Milky Way galaxy. The yellow dot shows where our sun is. And, I've often joked, Jeff, they really need to rewrite those scripts for the Star Wars movies because everyone shows up with this little piece of script, a galaxy far, far away.
Mm-hmm.
And we've been looking at galaxies far, far away.
Mm-hmm.
And we've yet to find one that's an adequate twin of our Milky Way galaxy to be a candidate for advanced life. And people say, well, have you really exhaustively searched all the galaxies? No, we haven't. And the farther away we look, the less detail we see. So that's a challenge.
Mm-hmm.
And you're also looking back in time. So you're seeing the galaxy as it was billions of years ago.
Right.
But the remarkable thing is there's now papers being published where they're saying, hey, we can look at a galaxy that we see it as it was 5 billion years ago. And based on the structure of that galaxy, we can predict what it's going to look like 5 billion years hence, assuming we get enough of a detailed map of what exists in its vicinity. So it's not like we're completely ignorant of what all these galaxies will look like. So, but the bottom line is this paper is basically giving us a stronger case. There's a lot more design in our Milky Way galaxy than we knew of 2 months ago.
Right.
I think this just got published. Yeah, it was published at the end of March. So until this was published, we knew there was design there, but this is actually making a stronger case that we really do live in a very special galaxy.
Very good. That's pretty fascinating, Hugh. Thanks.
Okay. Well, again, want to remind all of you that if you want to be kept up to date on stars, cells, and God, go to our YouTube channel. We archive all of the episodes, past episodes of Stars, Cells, and God on the Reasons to Believe YouTube channel. You can subscribe for free. And when you do subscribe, you will be alerted to all the upcoming video releases that will be there. And it's also easy for you to search through and find some of the past episodes, not just of this podcast, but of other podcasts we've done here at Reasons to Believe. And yes, RTB_official, that's your gateway to all the social media outlets of Reasons to Believe. And reasons.org, that's our website. And last time I looked, there were tens of thousands of articles there that you can access to get reasons to believe from the book of nature to give you confidence in the book of Scripture and sound reasons to give your life to Jesus Christ as Creator, Lord, and Savior. Thank you.